In this next section, we're going to talk about 5.2. We're going to talk more about electrons and to see what they are doing inside of each atom and how we can keep track of them, how we can organize them, and we can use that to predict a lot of properties actually. So we're going to start here in 5.2. Here's the vocabulary. And by the end of the section, you'll know more about all these terms. So we have the electron configuration, orbitals, suborbitals, quantum numbers, the noble gas notation, the Aufbau principle, Hund's rule, and the Pauli exclusion principle. Now, as we've talked about with the periodic table, is that it's arranged in a very specific way that it gives us a lot of information. And so, one of the ways that it's organized that we hadn't talked about is the blocks of it. We can actually break down the periodic table into different sections. And this actually tells us the electron orbitals that we have for each atom. All right, and so we can organize it by orbital types. And each section of the periodic table, we can think of it as a block. And you see that I have here the S block over here. That means that all the atoms on here will end, their valence electrons will be located in an S type of orbital. So for all the elements on this blue section, this is the P block of the periodic table, and all of the valence electrons for these elements will be located in a p orbital. Same thing for the d orbital. The transition metals are our d block of the periodic table, and their valence electrons will be found in a d orbital. And then lastly, we have the f orbital. Just like all the other ones, the valence electrons of these elements will be found in an f orbital. And so you can think of when we actually get to see the full electron configuration of an element, it's sort of like having an address on the periodic table. It tells us exactly what place it will be at on the periodic table, just through some simple counting. And then the only exception to this is really helium, because we're used to helium here being with the noble gases. It makes sense to put it with the noble gases, but when we're looking at the orbitals of helium, it's actually part of the s block. It doesn't have any p orbitals or d orbitals, so we just move it over to the left here to be along the s block. So this is really the one exception to all these different blocks of the periodic table, is that helium will be part of the s block, not part of the p block, as it's usually on the periodic table. Now, the way that the electron configuration is written is that we use what are called the quantum numbers, and these tell us exactly how many electrons we have and what type of orbital they are found in, what row of the periodic table they will be found in, and how many of them there will be. So now, what the configuration looks like written now. So let's say that we do the element of uranium. The electron configuration of uranium is this. And I know that you're just thinking, what the heck am I looking at? This is way too much information. I have no idea what all of these is. So not to worry. We're going to look at it all. We're just going to break it down to very simple blocks. And you'll see what each of these numbers mean. All right. Now, the reason that this is so long is that uranium has 92 electrons, and what this full electron configuration is telling us is the location of each electron. We know exactly for all of the 92 electrons of uranium, we know exactly its orbitals, we know its energy levels, and we know how many electrons are in each orbital. Now, the different quantum numbers, this whole electron configuration can just be broken down into three different parts that we just use over and over. So the first one is the number. So it's the large number we have. So on this one, 1, 2, 2, and 3. So those numbers, these represent the energy level or the row on the periodic table. So for these, let's start here on the left side. So I can have the 1s block here, 2s, 3s, 4s. Notice that I'm just counting down in order. So 1, 2, 3, 4, and 5, 6, and 7, all the way to the end. And then it does it on this side too. We skip the first row because there's no P block for the first row, but then we get 2, 3, 4, 5, and 6, and so on. All right, so that one is fairly straightforward. Next up, we have the letter, and this tells us the suborbital or the block of the periodic table. So as you saw over here, on the left, we have the S block in blue. On the right side, we'll have the P block. In the center here, we have the D block, and in the pink, this is the pullout section of the periodic table, which goes right between 57 and 72, 89, and 104. Is where we have these the rest of those elements. Those are the F block. elements. All right, so I should say that the one exception to this is the d orbital and the f block, d block and f block, where if we go back to that photo, you can see that we have the S block, we have one S. This is the first row in the S block section of the periodic table. Then 2S, that's the second row S block, third row S block, fourth row. Then if we keep going over here to the D section, we see that we have 3D, although it's in the fourth section. And so we could get into the really specific explanation for this, but it is just really complicated, and I don't think you're interested in knowing that. So for now, just know that when we get to the D block of the periodic table, we just subtract 1 from the row number. So we go from 4s to 3d, and then we go back up to 4p. Then the other exception for that is when we get to the F block. If we start here in the 6s, we keep going, we move on to the F block. Here we have 4f. So when you're dealing with the F block, subtract 2 from the row that it's in. So we go from 6s to 4f, then back up to 5d, and all the way to 6p. These are the exceptions, and so it'll just take some practice to get used to those. All right, but the last number we have here is the superscript. This is the number that's higher up, and it's written a little bit smaller than all the rest. And this shows us how many electrons are in that suborbital, if it's an s suborbital, p orbital, d orbital, whatever. We can also think of it as the placement of inside of that block. So if we have, the 2s2 orbital, we know that we are in the second row of the periodic table in the s block, and then we are in the second place. So it'd be 1 and 2 places. But I know it doesn't make a whole lot of sense right now, so let's actually look at some examples how we build each of these electron configurations to make some more sense of it. All right, so let's just start on this one very simple. We'll start with the very first element. We want to write the electron configuration of hydrogen. So let's see what things go into writing that configuration. So first we need to know the placement of hydrogen. So here it is, number 1 on the periodic table. It is in the first row, it is in the first column. So that's what we need to know. So it is in row number 1. So that means that we'll just start with the number 1 for our configuration. Next up, we need to know what block it is in. So you see that hydrogen is right here in the S block, so we'll just state that the block is S. Next thing we write is the letter of it. So far we have 1s for the configuration of hydrogen. And the last piece that we need is the placement inside of that block. So hydrogen is here in that first spot in the S block, so we will just say that it is 1, so we put in a 1 superscript for the place of it. So overall, for the electron configuration of hydrogen, we have 1s1. This is showing us that we have hydrogen is in the first row. It's located in the S section of the periodic table, and it is in the first place. Now, as I told you before, that the electron configuration shows us the placement of each electron. It also tells us how many electrons there are in an element. So in this one, because we have a 1 in the superscript, this is telling us that hydrogen will have 1 electron. And we know that from the periodic table as well. Remember that the number of electrons is the same as the atomic number. Hydrogen here with number 1, it has 1 electron. And in the superscript, we've shown that that location of that first electron. So it's all good on here. Next example is, let's look at helium. Now helium is over here. It is number 2 on the periodic table, but we'll go through the same process as we did with hydrogen. So first we need to know the row and the block that it's located in. So for helium, it is here in the first row, and it is in the S block. So we can start with that, writing 1s. And finally, we just need to know the placement for the superscript. So we know that it's in the second place. We can't be in the first place because that's the place that hydrogen takes up. But then helium will be in the second spot in the S block, so we'll write a superscript 2 in this. And now doing this, we are showing the location of 2 electrons. So the first one is implied to be in there already because we've already moved on to the second electron. So we already passed that, and we know that helium will have 2 electrons, and sure enough, we are showing the placement of 2 electrons on this one. All right, next, let's keep building up. Let's go on to the next one where we have lithium. Now, lithium is located right here, number 3 on the periodic table. So the same process that we go through as the first one. First, we need to know the row that it's in, so row number 2, and the block that it's in the S block. So far we know that it will be 2S, and finally the placement of it, it's in that first spot of the S block, so we'll give it place number 1. You write that out, it's 2S1. So we're showing the location of that electron of lithium. But the problem we run into in this one is that lithium will have 3 electrons. Here we are only showing 1 electron. So that's not matching up. We need to show the location of all the electrons that came before it. So in order to do that, we'll just put in the places that we've been through on the periodic table. Always start with number 1 with hydrogen and move to the right until you can't. Then you move on to the next row. So 1 and 2, that will take care of the first set of orbitals, and then when we get to number 3, we're finally to that 2s1 that we've already written. So we'll just add in the things that came before, so 1s2 for both hydrogen and helium, and then finally 2s1 is the location of lithium. So if you go through the superscripts and you add them, you will see that here we have 2 electrons in the 1s orbital, we have 1 electron in the 2s orbital. So overall, 2 plus 1 will add up to 3, so we are showing every electron that lithium will have. And then finally, let's go move on to the next one, sodium. It is right here, number 11, and we need to know the same information for it. We need to know what row it's in, 1, 2, and 3, what block it's in. It's in the S block. So far we can have 3S, and again, it's in that first place of the S block. So we are putting in 3s1 is the final location of sodium. But remember that you also need to put in everything that came before it. So we need to go through hydrogen and helium. That'll be 1s1. Lithium and beryllium, this is 2s2. And finally, we get through the p block. So now we put in 2p, and then the number of places we move through in the p block. So 1, 2, 3, 4, 5, and 6. So this is where we get that superscript 6 of 2p. So the full electron configuration of sodium will be 1s2, 2s2, 2p6, 3s1. And if you go through and you count them all up, if you count up all the superscripts, you get 2 plus 2 plus 6 plus 1. Total, that will be 11. So we are showing every electron that is contained within sodium. Now, let's take a step back and talk about why we are only putting in 2 electrons for the RS orbitals, but when we get to the p orbital, we put in 6. And so I mentioned this one a little bit ago, but I didn't go into details. Each type of orbital has a certain limit to how many electrons it can hold, and it really comes down to the number of suborbitals that are in each one. So for our s orbital, it can only hold 2 electrons, and actually our blocks of the periodic table show the same thing. For our s orbitals, there are only 2 places for the s block. Now when we get to the p orbital on the right side, there are 6 different places, 1, 2, 3, 4, 5, and 6, and so that's also the limit of the p orbital. We can only put in 6 electrons when we're talking about the p orbital. Now with the d orbital, there will be 10 places for the transition metals, so there will be 10 electrons that we can put in our d orbital. And then finally, for the f orbital, there are 14 places. We can put in 14 electrons for our f orbital. And finally, we get into the noble gas notation. So I think you'll like this one because it's really a shortcut way of writing out the electron configuration. If you thought that what we were doing before took a lot of work and it's really long, you're right. It is really specific, and we have this noble gas notation to make things a little bit easier on us. The way that this one works is that it takes the last noble gas that we pass on the way to the element that we're focusing on, and then we make that as an assumption that we are having the same electrons as that noble gas. I know it seems a little bit confusing, so let me show you how it actually works. We're just going to take a noble gas, and the way that it is written, make sure that you write it in the symbol for the noble gas in brackets. So these are the square parentheses. And then once we do that, we'll write the start over in the next row and show the rest of that configuration. So let's use the 2 examples we've used so far of lithium and sodium, and we can take these and put them into that noble gas notation. So if we're focusing on lithium, again, Lithium is right here in this third place. We want to start walking back and find the last noble gas that we went through. So from lithium, number 3, we go down to number 2. This is helium right here. So the way, if you wanted to write the noble gas notation of helium, you would just go 1s because helium is located in that 1s and it's the second place of it. So the noble gas, the notation of helium would be 1s2. Well, notice that we already have 1s2 in that configuration for lithium. So we're just going to assume all the electrons of helium, and we're going to say that by putting the symbol He of helium in brackets and then starting over in the next row for lithium. So we just need to go one place for this one, so we'll just say 2s1. So another correct configuration for lithium would be brackets He with 2s1 following after. And now finally, let's do sodium. Again, if we find sodium on the periodic table, number 11, let's walk back until we find a noble gas. So for number 11, we go to number 10. Here is neon in the 2p6 position. So notice that again, 1s2, 2s2, and 2p6 would be the configuration for neon, and that's already included in our configuration of sodium. So we can take this whole section, 1s2, 2s2, 2p6, and just replace it with brackets and E, and then we add in the rest of it, which would be 3s1 for the location of sodium. All right, and so I know that we've been over a lot of information and it can seem really overwhelming. So before we even get into energy, we're going to cut it off here. We're going to make a new section for energy. So check back on this later so you can get practice on the electron configuration before we even start talking about the energy of the electrons.